So in this tutorial, we're going to be taking the design we made last time, which I have here, and actually putting a motor into it. If you haven't watched the last video, I suggest that you go back and watch that now before we start. So to put a motor into our rocket here, you have to go over to the Motors and Configuration tab. So I'll click on that, and it'll actually come up blank at first for you. So if I do this, this is what it should look like by default. So click on New Configuration, and that's going to bring up this right here. And if you double click right here, you're going to get the list of motors that you can choose from. So by default, it should look something like this, where all the different manufacturers are going to be possible for you to select from. And it does by default limit the motor diameter to the motor mount diameter. So what that means is that it's not going to allow you to put in motors that are larger than the inner diameter of this motor mount tube here, but it will allow you to put in motors that are smaller, and generally we don't want that. If I just select something, say like this, that motor is way too small. It can't be held in by this tube here. So that one won't work. So usually I like to take this slider right here and drag it up so that the only option are motors that are 1.5 inches in diameter. You could also increase this, but then you're going to get motors that are like way too huge and never going to fit in your rocket, something like that. So if we just leave it like this, where we're only allowed to fit motors that, you know, can actually fit inside the body tube. And then what I like to do is, we generally only buy from Aerotech is where I like to buy my motors from, or possibly SDs if it's just a small one. So I'm going to hit this clear all. So that clears all the manufacturers, but then check off Aerotech. So now I have all the Aerotech motors listed, and you can do this for any of the motors, or any of the companies listed on here. So you have all your motors here, and there's a whole lot of stuff here. You have the manufacturer, the designation, the total impulse, the type, the diameter, and the length. So obviously the manufacturer is the manufacturer. The designation, though, each one of these starts with a letter and then a number, and sometimes it has another letter at the end that designates what kind of like burn type it is. That's usually something that's specific to the manufacturer, the final letter. So the first letter is the classification. So for example, I think I want to put in an H550 into this rocket. So you can see that this one does fit. And what this all means is the H is the class, so it starts with A. You can see it over here too. It starts with A and it goes all the way up through O. So each one of these is roughly double the power of the other. So a B is double the power of an A C is double the power of a B, or 4 times the power of an A. By power, I mean total impulse. So what is impulse? What it means in this case is the area under the curve of thrust versus time. So basically the integral of the thrust versus time function. Where you can see where that comes from is if you click on this Show Details tab right over here. This is the thrust versus time curve. So let me see if I can make that bigger. There we go. So this was input, you know, probably taken off of the manufacturer's website at some point, but basically all these little dots are where measurements were taken, likely during a static test, and you have your thrust in newtons and then your time in seconds. So basically at like 0.025 seconds, so a very, very short amount of time, it goes up to 650 newtons. So that's one reason I like the H550 is it's kind of more like a little bomb. I mean, it's done burning out after half of a second, roughly. It's burnt out. It's used all of its fuel in just half of a second. It just looks really cool, and it's really fun to fly and very loud. So that's one reason I like it, especially for a level 1 design. So the impulse is the area under this curve. So you could also have a motor that is, it's much shorter as far as the thrust, part of it, but it maybe goes for much longer in seconds, and then they would have the same total impulse. And that may, two motors with the same impulse, if one is, shaped more like this and the other is more, lower but longer, just because they have the same impulse doesn't mean it's going to have the same effect on your flight. One can make you fly, further and higher, and then the other could make you fly a lot faster. Generally speaking, if it's very steep and short, you're going to be going very, very fast, or at least at the beginning. If it's not very tall in the thrust dimension and very long in time, then you're going to be going higher, but probably a bit slower. You can also see these stats right here. So the total, again, it says the total impulse, 113 Newton seconds. So again, because that's the units here, newtons, seconds, the area is newtons times seconds. It's 96% of an H. So like, again, the letter is a classification, and it has like a specific, you can see right here when you hover over it, a class H is 160 to 320 newtons. 313 newtons is 96% of 320, so that's where that comes from. All of these classes have some sort of range similar to this, but generally scaled up. So like an O may have a range of like a few thousand newtons that could be classified as an O motor. Then you have the average thrust right here. So the average thrust is 553 newtons, and that's where the 550 comes from. So they just kind of round it off to usually the nearest 5 or 10 newtons or something around there. So this is where the designation comes from. The H represents the total impulse classification, and then the 550 represents the average thrust. You also have your max thrust, your burn time, the mass, and things like that. So we've got our motor selected now, and I'm going to hit OK. And then you can see now, instead of having NA or not showing anything at all for apogee, you actually, and all the max velocity and max acceleration and all that, you actually have some data in here that you can actually work with. And then also the stability has changed quite a bit. Before we added a motor, it was 1.92. I'm sorry, it was 2.88, and now it's at 1.92 after adding the motor. You can also see here where it says CG and CP. So CG is center of gravity. Again, the center of gravity has to be roughly, at least one body length diameter above the center of pressure, which is this red dot here. And then these numbers by default are measured from the tip of the nose cones. That's how far down the center of gravity and center of pressure are from the tip of the nose cone. There may be a way to change that, but it should be fine. So then this right here, it's very hard to read, but at m equals 0.3, so this is your stability at Mach 0.3. Your stability for the rocket really depends on how fast you're moving. And you can see how the stability changes over time during the rocket's flight, with changes in the motor mass and the speed and stuff like that, when we actually run the simulation. So what's posted here is generally considered the nominal data. If your stability is like right exactly 1 or only like 1.1 or something like that, yes, that is technically, good enough for the nominal data. But if you actually go and look at all the data points that were taken, you'll see that there will be large periods of time that your stability will be much less than 1, and that's not good. So that's just something to note. So 1.92, that should be good enough for us. Then the apogee down here, you see I'm reaching almost 2,500 feet, so it's about half a mile. That's probably fine. And then the max velocity, about half the speed of sound. That's probably fine too for a level 1 design. You don't want to go more than Mach 0.8 for this particular design because it has a plastic nose cone and some other things that could break if you go supersonic. But if you replace this with a fiberglass nose cone and use some very extra strong epoxy in this area, you might be okay. I'll get into that probably in the next video when I talk about converting this to a level 2 design. And then you have your max acceleration down here in feet per second squared. So now that we have a motor added to the design, we want to actually see, we can see these numbers here, but it's still always good to do an actual simulation. So if you go over to this flight simulations tab, and you can click on new simulation right here. Now, this is going to bring up a whole bunch of stuff. So first thing you'll probably notice is the wind and weather conditions here. So the wind speed that comes up here is just what OpenRocket generates by default. Generally speaking, a lot of launch sites are not going to allow you to launch if it's more than about 15 miles per hour wind, depending on how much space they have and such. But I'm just going to leave it as the default for right now. And then this may be something you actually change when you get out to the launch site. If you uncheck this box, it'll allow you to change temperature and pressure. So this is just the standard atmosphere and pressure, 70 degrees Fahrenheit, and then standard pressure. I think this is standard at sea level or roughly. But if you're launching, say, at like Spaceport America, your pressure and temperature are going to be a lot different because you're way out in the desert and you're 5,000 feet above sea level. So then the other thing is this launch site right here. I generally don't mess with the latitude and longitude. That doesn't really matter for the heights that we're talking about. You're not getting anywhere close to space or anything like that. But the altitude of the launch site does matter for sure. So 4,500 I have entered as my default because that is what I was using for simulations of the Spaceport America rocket that I was designing. But out here where I am, I'm in Ohio, it's generally about 500 feet above sea level. So I'm just going to put it to that. And then the launch rod length I was using at Spaceport America was about 17 feet. But for a rocket of this size, you're not going to be using a launch rod much longer than 6 feet. It's probably going to be more like 5 feet, so that's what I'm going to do right there. 5 feet, and note that I changed this to feet. It is inches by default. And then I'm just going to leave this as it is for the launch rod angle. Generally, they just point them, straight up perpendicular to the ground. That's how it's set right now. So this right here is where you can select between other configurations of motors that you want to test. You could just change it out really quickly. Right now we only have one. And then over here in this tab, simulation options, this is more advanced stuff. You don't have to worry about this too much. But what you can do is you can set this to be, smaller amounts of time if you want to get like really, really accurate. And then there's other sorts of things here. This has to do with like differential equations and stuff like that. And then if you wanted to add some other functions that maybe you wrote, like a program you wrote, you can add those here. But I generally don't mess with any of this stuff. So back to the launch conditions. I think now we're ready to hit simulate and plot. So once you hit that, this box will come up and you'll see you have a whole bunch of different variables that you can actually plot here. So by default, it's plotting time on the x-axis and altitude, vertical velocity, and acceleration on the y-axis. And these are the units here. And you can remove these if you want by clicking this button. And then over here, the flight events, these are what is going to be marked on the graph. So motor ignition, motor burnout, apogee, recovery device deployment, and ground hit. So, and you can also check off all of these or, different ones and things like that. And you can add more plots. So one plot that's usually useful, and you add that by clicking this new y-axis plot type. You can't add more plots to the x-axis, at least in this configuration. So to change what you're plotting, you can click on this drop down, and there's a whole bunch of stuff. There's like 50 some odd variables. So let's say one really nice thing to plot sometimes is your stability margin calibers. So that's going to tell you like how stable you are at certain points, but it's hard to look at those stability margin calibers when you are also plotting altitude, vertical velocity, and vertical acceleration, because altitude, vertical velocity, and vertical acceleration are on the order of like, you know, times 10 to the second, or times 10 to the third, or even times 10 to the fourth, whereas stability margin calibers are always going to be somewhere between like 1 and 3. So it's just going to look like basically a flat line at 0 if you plot this while you're also plotting these 3 other variables. So for right now, I'm not going to plot a 4th variable, and I'm going to remove that. But you have the option to if you want to. And you could always remove all of these things and then plot stability, and you'll actually be able to see what's actually happening. And then the other thing you can do is export data. We'll get into that after we look at this plot. So I'll hit plot right now. And this comes up, this window right here. So this is basically the red line is your altitude, as you can see here. Then the blue line is your vertical acceleration, and the green line is your vertical velocity. And then you can see the flight events. Motor ignition is kind of hard to read, and the motor burnout right after it. We have apogee and recovery device deployments happening at the exact same time, because that was the settings that we put in for the drogue parachute, if you remember in the last video. So you can see that here. And then you see it's basically falling at a pretty much constant rate until the main chute deploys, and then it slows down a lot more. You can also see that in the vertical velocity. After the main chute deploys, it slows down quite a bit. So if you have a graph where it's really, really shallow, the red line is very, very shallow, your altitude, that's generally there's something wrong. So a really steep line like this is really what you're looking for. In this case, this rocket reaches apogee in about 10 or 11 seconds, I guess. So I can close out of there, close out of here, and it's going to give me a summary of the data basically that we just simulated. So the velocity off the rod is really important, 103 feet per second. Generally, there's going to be no questions asked. If you're showing this to somebody who's running the launch site and giving you your certification and it's 103 feet per second, there won't be any questions asked as long as you're over 100 feet per second. If you're less than like about 70 or maybe 60 feet per second, they're going to be really questionable about, you know, if your rocket is actually going to work or not, because you need that speed when you're getting off the rail to keep your rocket stable. And we can kind of show you that when we export the data here. Then of course apogee is also given. This is the velocity at the deployment of the main parachute, so it's 49.2 feet per second. There may be, like when you're purchasing a parachute on the manufacturer's website, there may be like a maximum velocity it can deploy at without braking or something like that. So that could be something you want to look into. But I think for this design, 49.2 feet per second is probably okay. Optimum delay. This is important for if you have, excuse me, if you have a motor that has an ejection charge on it. And the H550 does. Like, we don't have any electronics bays or anything like that. So we need the H550's ejection charge to pop out the parachutes. So what this means is that the delay that you want to set for the H550 is 10.7 seconds. It comes with a maximum of 14 seconds, and then you can take your the little drill that you get in the kit to drill out part of the ejection charge so that it burns through a little bit faster. and then you can drill that down to probably around like 11 seconds, and then have the ejection go off right at apogee, which is what you want for the drogue parachute. And then you have your max velocity, and sometimes these are like very marginally different, the max velocity and max acceleration, and apogee as well, as to like what is said down here, because this down here may depend on like some of your default settings, and it also is not going to account for wind or any of that other stuff that you put in, but this does. So the default I have for my launch altitude was 4,500 feet above sea level, but I changed it to about 500 feet. So that's why the altitude here, 2,475 feet, decreased by about 100 feet because of an increase in air pressure when you lower your launch site altitude. So that's why it's a little bit lower here. And then the speed is also a little bit lower, again, because of an increase in air pressure and air density than it is down here. Acceleration is also a little bit lower, just very marginally. And then it also gives you the time to apogee and the flight time. And then finally, the ground hit velocity. So this is important because, generally speaking, as a rule of thumb, you don't want to hit the ground at more than about 20 feet per second. 17.1 feet per second should be fine. You also don't want to be hitting the ground at less than like about 10 feet per second, because that means that you're moving really, really slowly under your main, and you've probably bought a main parachute that's too big, and your rocket is just going to fly away and like get stuck in a tree or something, and or take forever for you to get it. So 17.1 feet per second is good. So now the next thing you're going to want to do is export the data. So what I'm going to do is click on this plot/export button while I have this simulation selected. So again, this is going to bring up this same thing right here, the same window we saw before, but now I'm going to go over to this export tab. And what this is going to do is it's going to take all of the data that it used to make that plot that we just saw before, but it's going to put it into a CSV file. So something that you can open up with Excel and look at all the individual data points, and it's really, really useful. So I already have a bunch of variables selected. I've selected time, altitude, vertical velocity, and vertical acceleration. I mean, for anything that you're going to be plotting, I always suggest doing time and altitude. No matter what other variables you're plotting, you should always at least do those first two. So time, altitude, vertical velocity, vertical acceleration. There's a whole bunch of other stuff. And then mass and propellant mass was another thing I wanted to plot. And then stability margin calibers, Mach number, which again, this, for example, reaches up to Mach 0.74, so or 0.47, so that's 47% of the speed of sound. And then thrust in newtons, drag force in newtons, because when I was doing this before, I was like worried about, you know, what the drag forces were on the fins. So I wanted to plot drag force. And by the way, the drag force that you plot here is the total drag force acting on the whole body, not just the force on the nose cone or on the fins or other things like that. And then, let's see if I plotted anything else. And then that was it. So that is all the variables you want to plot. It'll also show you how many you have. You're exporting 10 out of 54. And then we should be ready to hit export now. And it's going to come up with some place to save it. So I'm just going to save it as test. And there we go. So now what I've done is I've gone and opened up the CSV file in Excel. So we can see that this is all the exported data. We've got time, altitude, vertical velocity, vertical acceleration, all that stuff. And then here we have the events. So event launch is, well, when the rocket, you know, takes off, and then ignition occurs at the same time. They both occur at t = 0 seconds. And then liftoff just as soon as the rocket starts to move off the pad. And then launch rod is as soon as the rocket actually moves off of the guide tower, basically. So we can see that our velocity off the rod is 103 feet per second, which is what we've already seen in open rocket. But what we haven't seen is the stability margin caliber, which is in this column here, the stability margin caliber as soon as it leaves the rod, which for the condition of the default wind speed setting, which was like 4.47 miles an hour or roughly 5 miles an hour, is about 1.37 for the stability margin caliber, which is totally fine for our purposes. And then you also see some other things like drag force, for example, that usually gets to its peak during the rocket's maximum velocity phase, basically. So the drag force for this rocket got up to be about 40.4 newtons when the velocity was at its peak. So then the other thing I've just done is I went back into Open Rocket and I made another simulation with the wind speed being 20 miles an hour, and now I've exported that data and I want to take a look at what the difference is between those two wind speeds. So I copied that into another sheet here, and we can see that the vertical velocity, according to Open Rocket, has gone up from 103 feet per second to 190 feet per second. I would take that with a grain of salt, certainly. I can't really explain why Open Rocket thinks that the velocity off the rod would increase by so much due to an increase in wind. But it is certainly still more than 100 feet per second. This is still perfectly fine. Now you see over here that with the increase in wind comes a decrease in the stability margin caliber. So instead of the 1.3 off the rod, again, this is stability margin caliber in this column, instead of 1.3 off the launch rod in the last simulation with a wind speed of roughly 5 miles an hour, we're down to 0.68, which is in normal conditions not good enough. However, you can see that the stability manages to correct itself to about 1.17 within, like less than a tenth of a second after leaving the launch rod. And this vertical velocity makes up for that lack of stability at the beginning. And we can also see how the wind has affected the apogee altitude. If we keep scrolling down, you'll eventually see apogee. So the apogee is at 2,456 feet, whereas with the wind speed of 5 miles an hour, see where the apogee was, 2,354 feet. So the wind actually increased the apogee slightly, possibly because it was making more air move over the fins, which was giving the rocket a little bit more lift or something along those lines. But it doesn't have that huge of an effect in this case. So that is basically everything for simulating a level 1 rocket. It's pretty simple. Just make sure that when you're launching the rocket, whoever is in charge of the launch site checks all this out and okays it. And if your design is, similar as far as stats and things like that, as far as how fast you're going and how high, you should be good to go. I'm not saying copy mine completely. You should definitely do something different. At least try, something, even if it's just a small thing that's different. But yeah, if you follow this general formula, you should be set. So yeah, that's all.